So I'm streaming now. Oh, but it's not showing me my live status here. I mean, like I can see that I'm live, but on my channel I can't see that I'm live. That's sort of weird. Hmm, I don't like that. Because if you don't know, if you're just like now started watching the stream, I was streaming for past, what you might call it, 30 minutes. And I just got to realize that that stream's not even live. Yeah, it's not. It's just not live here. God, that's a bummer. Well, anyways, now it is live. I know it's live. So let's move on. We went through Moore machines, melee machines, some differentiation, the differentiating factors in that. In building FSM's logic gates, you must assign binary codes to your symbolic states, generally the number of possible states is 2n, where n is the number of flip-flops. However, an alternate method is one-hot coding. I know if it's simpler as the design procedure and leads to faster next state logic, making it highly effective for flip-flop rich architectures like FPGAs. Okay. God damn it. Let's just put this here. There is a real storm raging on outside. I can tell you that much. The stream disconnected for a second. Hmm. Okay, well that's done. Let's see what else is here. Well, that's my Duolingo. God, I'm starting to hate that word. By the way, did we write down that FSMs only work for the positive edge, one positive edge cycles, they're synchronous machines. Let me see if we wrote that down. I don't know if you have though. Combination logic, blah blah blah, circle states, blah blah blah, blah blah blah, blah blah. Sequential. They are what did we call them? Asynchronous. Yeah, synchronous. We have not. Okay, okay, interesting, interesting. I don't know why it hasn't talked about that. It should have, but yeah, they're synchronous. They only work on positive head cycles. You know what? Let's just pause it. Pause. Edge cycles. Probably add more to this if there is anything more to add. That is what a little while later. It's from 28th April. But there are notes before this. Let's see. We haven't learned about STDs. That's state transition diagrams. Well, I guess we have actually. Oh, we haven't labeled them. So they are called STDs, state transition diagrams. Where did we do these? I have zero goddamn clue where we did this. Let's just write this, I guess, here. STDs, state transition diagrams. All right. Keep moving forward. Well, I think it's time to send a new batch of photos to Gemini and we'll see what the hell it makes of it. At the end of the night. Make no mistakes. That's like the official period marker of my prompts, of all of our prompts. Um, there's a lot of code. I don't like coding. I really don't like coding this. Shift right. think I want to start another notebook for this. So, no, over here I'm not going to be using my own notes. I'm going to be using other people's notes. So other people's notes. So I'm going to write. Perfect. We're going to be discussing about this is I'm so tired. But the show must go on. This page outlines the complete design process of a three-stage finite state machine moving from a state transition diagram to STD to a final Boolean equations. The state diagram, you have three states: zero encoded as 00, change encoded as 01, and one encoded as 1 state transition. The system moves from 0 to change when the input 1n is 1. It moves from change to 1 if the input remains 1. The input drops to 0 at any point in the state. The machine resets back to 0. So the system moves from 0 to change. When the input is 1, it moves from change to 1 if the input remains 1. If the input drops to 0 at any point, this machine resets back to 0. That's pretty straightforward, I think. You mapped out the present state, the input state, and the next state, and output. Let's actually check out how we did that. So 0 remains 0, 1, 1 equals the change state, and again 1, that's the output 1, okay. Sequential circuits used for representation for designing sequential circuits. As with all sequential circuits, output depends on present and past inputs. Hold on, let me just let's do one thing. Let's do this. Oh damn, what is this? Ooh. Yeah, this is new stuff, okay. It's not showing up. God, you can't see it. Okay. That's intriguing. It is showing up. Okay, okay, so you can see this all. That's great, that's great. Used for representation for designing sequential circuits. As with all sequential circuits, output depends on present and past inputs. Effects of past inputs represented by this current state. Behavior is more from cycle. Behavior is represented by state transition diagram. Transverse 1 edge per clock cycle. That's important. Flip-flops form state registers. Number of states is less than equal to 2 number of flip-flops. Okay. Again, that's important. I don't know why the hell we haven't been writing all this down. Combinational logic calculates the next state and output. Combinational logic, which is the current input. Okay, yeah, that makes sense. Sim follows exactly 1 edge per cycle. I think this is quite important. We should add this to our notes. However late that might be. Our parity checker. A string of bits has even parity if the number of ones in the string is even. The design is circuit that accepts an infinite serial stream of bits and outputs a 0 if the parity thus far is even, and outputs 1 if odd. So we have to output 0 if even. That means if the number of bits is even, and 1 if it's odd, if the number of bits is odd. Bit stream in the clock output parity checker. That's pretty straightforward. I think this is a high-end diagram, high-level diagram. Even, and as soon as we go into odd, the in changes and the output changes at the clock cycle. Okay, and then it what is it decrease in the middle? There's one more and that's even. Okay, okay, and then one more, and then that's odd again. That's odd. And since it's odd, our output will be 0. So it sees that. No, 0 if even, then it changes again to odd. And it changes to 1 again. Then decreases 0 odd. So the input is God, I don't understand the input logic. Okay, it remains odd. So it remains odd. It remains odd. 0 and then 1 even. Okay. By hand design process, bitstream in Each cycle circuit is in one of two states transition. In each cycle, with each movement over exactly one arc. Output depends on which states the circuit is in. By hand design process, part B. State transition table, even, blah, 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 blah. What the God, this is annoying. Invent a code to represent the states. Even, odd, in, out, in, out. Derive logic equations from table. How? Yeah, that's a good question. How the hell do we do that? I think we probably should put all of these maybe somewhere here. I don't want to put them. Okay, let's just leave them at the end. What the hell? By hand design process, logic equations from the table. Out is equal to the present state. I guess next state is equal to present state, exclusive or inside. So with this, we create our circuit diagram. Which I can put this right here. Formal by hand design process. What the hell's the difference? I don't know. Let's see. Specific circuit function in English draws STD, state transition diagram. Write down symbolic state transition table. Write down encoded state transition table. What is encoded state transition table? Interesting. Let's go back. By hand design process encoded. I guess this is encoded state transition table. Drive logic equations, drive circuit diagram, and register to hold state. Combination logic for next state and outputs. Okay, boss. Whatever you say. Whatever you say. Combinational law, for example. I don't know if we're actually doing this right now. We'll check up on it later. First of all, let's see what's this got to do next. Where were we? Okay, K-maps and equations, okay. K-maps and equations. Practical applications, 4-bit SPI receiver, that's image 2 and 3. Let me just quickly input those. Yes, just goddamn, just do it, yes. Again, these are not my notes, they are from a friend, because I did not attend the classes. So what does it say? These pages introduce a major practical engineering concept, an SPI, serial to parallel interface. The objective, you need to design a circuit that takes a serial string of data, one bit arriving at a time over a single wire, and package it into a 4-bit parallel output. The timing diagram we drew a bit stream. The note, okay, do we have any, what you might call it? Notes for this, or slides for this one. Combination of logic after this process and expectations. It's 9:30 already. I mean, like, what else? Tomorrow we will probably do apply probability. Yeah, probably. I'm gonna, you know what, let's do from tomorrow 9 to 12 p.m. Or, sorry, a.m. Yeah. So an early morning stream to get those out of the way, because, again, I do have another, what you might call it, quiz or exam related to that. So we'll do that. Data depth and controller. GPT will encounter additionally if you are looking to implement this in code the system or allow PPT provides an actual system or code for serial in, serial out, shifter format. That is great. That is great. That is great. We have actual work on that. You drew a bit stream. The note to work after start with 0 is crucial. Serial lines often idle I at 1. The first 0 tells the system, wake up, the 4-bit packet is about to arrive. Alright. Let's do a screen on this. Give you all this one. At the end of the story, you will meet someone to worry. Where did we leave off? It was on architectural separation. Then let's go on to this. Data path and controller. Let's add one more. I think we have room for one more. SPI control. Oh, that's another image. Okay, yeah, let's hold off on that, I guess. 1, 2, 3, 4, 5. That's image 5. Is that really image 5? One, 2, 3, 4, 5. Or is it from here? 1, 2, 3, 4, 5. That seems to be it. I don't know. That's just, I'm saying this because that's like literally just this diagram, but Gemini has created like a healthy looking paragraph for it. You need to design through architectural separation image 3 to build this. You separate the design into data path and controller data path components. This contains a shift register which physically slides the incoming bits into a 4-bit block and a counter which counts how many bits have arrived so the system knows when it has to collect. This is the controller. This is an FSM that manages the operation. It monitors the data in line and the controllers and the counters down count. It outputs control signals shift in telling the register to accept a bit. And counter resetting the counter for the next packet. I'm going to be honest, I do not understand a bit of this. Oh my god. Simple interesting, specific focus on melee machine notation and logic. Melee notation, you do states 1 and 0. The arrows use the notation in and out. For example, the arrows looping on the One state stay one, meaning if the input is 1, the output is 1, it stay in this state. Flip-flop manipulation at the top, you know, blah, blah, blah. Logic derivation, you build the truth table for the Mealy machine, you use the tool variable k-map, you extract the combination of logic required to build it. Perhaps looking at where the hell is my phone? That's the one. Giving me all this. God damn it. This might be a lot bigger thing than I sort of anticipated as. Ouch. Okay, so how are we going to do this? How are we going to do this? How are we going to do this? God damn it. This contains a shift register, which physically... Where's the shift register? In the block diagram, the shift register slides the incoming bits into a 4-bit block and a counter, which counts how many bits have arrived, so the system knows when it has collected 4, and then it goes and it delivers that 4-bit sort of like packet into a 4-bit data packet. Yeah, that makes sense. This is an FSM that manages the operation and monitors the data inline and the counter's down count. It outputs control signals shift n, telling the register to accept a bit, controller reset, resetting the counter, controller out, controller reset. Okay. I think these are notes. I also might have slides related to this, so we'll do the slides as well. Let's finish this. I mean, like we have until, I'll say that we have until 10, so roughly about 23 minutes. SPI controller. This page is the actual state diagram for the controller mentioned in image 3. It governs the logic of SPI receiver. Wait state, the system idles here. Data ready 0, shift equals 0, the counter is reset. It stays here until it is seeing the starting bit, which is of course 0 because it remains at 1, which is a high state, load state. Once the data bit is detected, it starts here, shift encoder turns on. The system loops in this state, pulling in bits as long as the counter has not reached a 0 state. If it's not received as 0, down count is not equal to 0. Okay, so I understand, since down count is not equal to 0. I still don't understand. No, I was lying there. I was completely lying. I do not understand. If the start is 0 and the end is 0 and the only possible logical inputs according to that theory is 1s, then why even have an input? Because all of the inputs will be 1s. Ready state. Once 4 bits are collected, the machine jumps to a ready state, signaling that the parallel data is available to be read by the rest of the system before cycling back to wait. So I guess what happens is 1111 after 4 bits of packet is compiled, we stop and we say, hey, this 4-bit packet is complete. I'm going to stop here and work on another 4-bit packet. And when it says to stop, it goes to the 0 state to the wait state because it detects 0-bit, a downshift, a down count. That's what I learned. So now images 6, 7, 1, 2, 3, 4, 5, 6. And why is this? Copy image. Yes, just put it down. Just put it down, don't worry about it. Rotate left. No. Rotate left. I could have just flipped horizontally, but no. I had to make it a target. Copy image. So what images 6, 7 tell us is a few things. These pages walk through simpler two-state machine, which specifically focuses on Mealy machine notation. Yeah, because I believe everyone's... No, it's in the arrows. The output's in the arrows. That's Mealy machine notation. I may be wrong on that. I really don't remember. Let's double check, you know. That's why we have all of the notes. So Moore versus Mealy machine states that if output is encircled in Mealy machine, if output with arrow, and then Mealy machine. My mouth becomes so dry while this speaking. I'm probably gonna be streaming Rivals after this. Just fucking a few freaking hours of Rivals. You drew the states 0 and 1, the arrows used in notation, and now, for example, the arrow looping on the one state states 1 1, meaning if the one output is 1, if the input is 1, output is 1, and stay in the state. I don't understand this. But we're making notes, we'll understand it later. That's the point of it. Flip-flop calculation at the top, you noted the formula for determining how many flip-flop bits you need for your state memory. Log 2 number of states. For 2 states, you need exactly 1 bit. Sort of like the same philosophy of normal bits, like the 2 raised to power n type of bit, which was like sort of like hinted to or stated in, I think it was actually stated in the slides that we copied. Logic derivation, you build the truth table for this Mealy machine using two variable k-maps. You extracted the combination logic required to build it. And as to 1n, states are entirely dependent on the input, bypassing the present state. Output logic is equal to the input into the present state. I don't know what the present. Okay, this. Let's move on to slides. I cannot write for the life of me. Is that really the best I can do? Yeah, that's the best I can do. Data pattern controller. Now we're looking at this. Design a 4-bit SPI which takes and streams bits serially one at a time and makes 4 bits of data available These 4 bits of data available. And the output in parallel. Things to think about. What hardware components are required? Shift, shift register, counter, controller. What are the specs of those? Data path, elements, high level, and low block diagrams. I have no idea. What is this? I don't know. I don't know. What is this all? Data path and controller. That's a really complicated piece of imagery. I do not understand what's going on here. Design a 4-bit SPR which takes in stream of bits serially one at a time and makes 4 bits of data available at output in parallel. Things to think about: what hardware components are required? Shift register, counter, and controller. What are the specs of those data path elements? Oh God, the UART protocol. Do we have to do this right now? I actually don't know. No, I don't think we've done this right now, so thank God. I really don't think I've done this. We have done this. Counter, controller, blah blah blah. Looking trial to implement this code. System will provide the actual system will allow code for serial in. Wait, what are you seeing right now? Oh God, that's not good. No, 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 no. Well, it's okay, but you just can't like look at all my tabs, you know? That won't be good. Teach it to me in concise goddamn notes. So 4-bit SPR receival overview. It receives a stream of bits serially one at a time and makes 4 bits of data that are available at the output simultaneously and in parallel. A serial parallel out register that acts as the main data path element to capture the bits, keeps track of how many bits have been shifted so far. The state machine then manages the control signal for the shift register and the counter. Shifted inside a shift register. God, I don't understand. I'm sorry. I don't understand this. Keeps track of how many bits have been shifted in so far. The state machine that manages the control signals for the shift register and the counter. To sequence operators, the FSM controller relies on 3 primary states. Where the system is here while the data. While the serial input is high, the transitions when a start bit is detected in this state. Shifting is disabled, shift enabled, and the data is not ready. Controller turns on the shift enabled and starts the counter. It loops in the state, continuously loading bits until the counter reaches 0. Ready shifting stops and the system flags that 4-bit is complete. 4-bit word is complete. The system then loops back to the bit machine to prepare for the next transition. The shift. God, how the hell would I do this in the year? I don't know how I'm going to do this in the exams. Module definition grade requires inputs for the clock. Reset. Serial line. Data in and shift enable in. The output is 4-bit parallel bus. Flip-flop logic it uses on the passage. God, I don't know what the hell all this shit is. Let's just go into system log files and see ourselves. Let's see ourselves what the hell this is. System Verilog. Parameterize modules, vector subfields. Vector subfields. I don't know if we've done vector subfields yet. But parameterized modules, local. You're still looking at, yeah, local parameters. I'm just looking at all of the other sources to see if there's anything else I could like possibly use to understand this better. Local parameters, like, oh shit, there's a lot of system Verilog stuff that we have to do. Instantiating a parameterized module. Type def and enum. System Verilog code for architecture of the machine. System Verilog code for serial and parallel out shifter. There you go. Here we got it. And this is the last one that we have. Okay, interesting. Let's just add this. I guess I'll add this because this is sort of an overview of what we've already done for our, what is this? What's this called? Our 4-bit SPI receiver, yeah. Oh, it's here, sorry. Oh, wrong place. Two-state melee machine. These pages walk through a simpler two-state machine. Let's see if there's anything related to these in my slides. Two-state melee machine, anything related to them in those slides? I do not know. At the end of the story, related to two-state melee machine. System Verilog, I think I really need to sort of like put in work towards System Verilog. That's all for tomorrow. I think tomorrow is a heavy case of what you might call it. Streams. I think I'm gonna stream a lot tomorrow. So tomorrow we're gonna have a DSD stream, we're gonna have an AP stream, probably gonna have an EM stream, electromagnetism stream. What else? What else? Possibly, you know, what the freak is that? I'm sorry, I think I just saw something. There's something in my. That was that? You, that's disgusting. Is that just like a dust bunny? Let me check, let me check. What the hell is that? Oh my god, oh my fucking god, oh my fucking god, oh my fucking god. I have zero clue what that is. I'm sorry, I have to check this out. At the end of the story. Oh shit. Oh shit. It was a pin. Should not have done that. Should not have. But the energy still works, so who gives a damn? It still works. If it ain't broke, even though you just broke it, don't fix it. In which, what you might call it, which source? You know, let's just turn. I really don't want to turn off. God damn it. At the end of the story. FSM2. What the hell? There's an FSM. There's a second PDF? Oh my god. So that's FSM1. Oh, I didn't even see this. There's an FSM2. Oh my god. But we haven't done combination locks here. Or is it a combination lock? Intriguing. FSM implementation notes. Guess what? I found more slides. Yeah, I found more slides. Finite state machines as detectors. Design a circuit that asserts its output for one cycle, which when the input bit stream changes from 0 to 1. So, okay. Interesting. You know, let's do one thing. I know what to do. For future me, let's write further slides. No, let's just put up slide 2. Why not? Look at these. Transition state diagram, solution A, more. Solution B, melee. Architecture timing diagrams, all of this. Beautiful crap. FSM comparison, more machine, blah blah blah. Final notes on Muller versus melee state assignment. What the hell is state assignment? One hard encoded FSM. Finite state machines, CL block, architecture example. God, that's a lot of stuff. That is a lot of stuff. No, you can't watch that. You can't watch that. You didn't see nothing. You didn't see nothing. You did not see anything. Let's just upload these files. I'm uploading these files to Gemini and seeing like whether it can tell me what's important. Okay, it's 10:01. Let's start to wrap it up. Just a few minor things left. I'll just write down the slides. When we'll come back, I don't know when I'm gonna come back. Probably tomorrow. Yeah, I'm gonna try tomorrow. Maybe even at night now. I really don't want to do it at night. Ew. I don't want to do it at midnight. So let me just think what's left. We have. God, how do I handle like my body's so tense? I want to handle that stuff. I don't want it to be tense. So we can handle that by. I'm gonna meditate obviously, but I'm gonna see how much DSD we actually have to do. We have to do until FIFO and UART. Oh God, that's another thing. FIFO and UART. Okay, deep dive into one hot encoding. In one hot encoding, you use exactly one flip-flop per state. So let me just check on a few things. Finite state machines, bit solar received one at a time. Finite state metastability. What the hell is this? State transition diagram, stuff like that. Bullshit. Output should be 1 minute. Okay. Interesting. Maybe the notes are jumbled. Maybe the images that are uploaded are jumbled. Well, that's why we make notes, so that the final notes are not jumbled. Moving from state A to state J. One which is blah blah blah. And awkward rule of thumb. White costs in general for purposes slide notes that more misbehave. Self-block rich, making it one hot encoding very common and a practical approach. Part. How to actually write these state machines in Verilog. We discussed standard Verilog relies on local param. The default trick demonstrates a highly efficient way to write the always block by utilizing blocking assignments. You can write the normal values like out one, next state idle at the very top of the block. Then inside your case statement, you only have to specify exceptions to those normal values. This makes your code much cleaner and prevents you from accidentally inferring unwanted latches. What the hell does inferring mean? Inferring. Inferring is the cognitive process of drawing logical conclusions, being educated. This is a driving meaning based on evidence reasoning. I just read that. I did not digest any of it. Is the cognitive process of drawing logical conclusions, making educated guesses. Basically, just using any extra latches. That's what I understood. What do I want? What do I want? I mean, like, maybe we don't need the slides to be in our OneNote. Maybe we can just learn from the slides. We'll offer some implementation notes. All examples so far generate output based only on present state, commonly called a mood machine. You know, let's do one thing. Tomorrow we're going to go through all of this. Yeah, that's good. But before we stop, I want to send in the rest of my... Well, hold on. You can't see this. You can't see this. Oh, no, you can see this. Apologize. You just can't see it. I'll apologize. It's private information. Yeah, there has to be some boundaries between us. You understand? You understand, don't you? Continuations. At the end of the story. The coil is burnt to bits. And my water bottle. And my water bottle is empty. And my water bottle is empty. Let's see what this has to tell. Based on these specific handwritten pages, you are putting theoretical FSM concepts from your lecture slides into concrete. Practical practice as requested. There is a high-level list of all the topics covered across these 5 images. Defining the behavior of a circuit that detects a 0 to 1 input transition Moore machine. Edge detector concept, Moore machine, detector, edge detector, K-logic, minimization, combinational logic circuitry, Mealing machine, edge detector, synchronous versus asynchronous timing analysis. Let's see if there are any sources related to this. you know what? I don't think that there's anything else we're gonna be discussing. So, especially on our OneNote. So we'll end here. Hope you I don't know what else to say. I guess it's not like a traditional stream where I try to teach you all, but let's stop it right here. Okay, goodbye.